Welcome to another lesson in Advanced Topics in Chemistry. Notice the title of this lesson is, or part A of the lesson, is on exceptions to the trends in ionization energy across periods. The overall lesson is on ionization energy. Maybe I should just take a moment and remind you what ionization energy is. Ionization energy is that amount of energy needed to remove a specific electron from an atom. It's typically, the units are generally, it could be other units, but kilojoules per mole is the typical unit, meaning that you need a certain amount of energy for every mole of electrons that you wish to remove. In the first case, we are merely talking about what we call the first ionization energies. Remember when I said a moment ago, when I say ionization energy, I'm referring to a specific electron. In the first part of the lesson, we're only talking about the first ionization energy for each element, meaning we're talking about the amount of energy needed to remove the outermost electron from, the outermost shell of a given element. Now, if you look at this graph is in terms of atomic number, the first 19 elements, and we are graphing that against ionization energy expressed in volts. Notice here that for atomic number 1, we have a specific ionization energy. For 2, we have a higher ionization energy for helium. Then notice we have a plunge all the way down to 3. What's happening there? Well, it turns out that there's a pattern, a general pattern, across periods. From hydrogen to helium, that's period 1. So notice as we go up, or go across period 1, we have an increase in ionization energy. Notice here, we've left period 1 and we've gone to period 2. And now that we notice a similar trend, not exactly the same, as I go across period 2, from lithium over to neon, I have a general increase. Well, we have some exceptions. We're going to talk about why there are exceptions. Likewise, if I look at the elements across period 3, I likewise see a general increase in ionization energy. So if you notice, I already have the notes written out here. The general trend in ionization energy across periods, that's not helpful. Helpful update? No, I don't think so. With increasing atomic number in a period, ionization energy increases, as I said over here and here. Now, of course, I said that there was a general increase. Well, why don't we look at the places where we have a discrepancy? One way to look at the discrepancy is this. If you notice element number 4 and element number 12, we can think of it this way. These are a little higher than they ought to be. Why do I say ought to be or expected to be? Because if these were a little lower, let's say if it were here, or I should say here to make my point, and I should clean it up a little bit. If it's here, notice then that we have a steady increase. That also applies over here. If this one likewise, this is element number 7, and then this is element number 15, we can also likewise couch it in these terms that these elements have a higher ionization energy than we might expect them to have. Again, if each of these were a little lower, we would not just have a general increase in ionization energy, you would have a uniform. You would always have just an increase with no exceptions. What could possibly explain why the elements here and here, by the way, these are both in period, or I should say these are both in group 2, and these are in group 15. So there's something about elements in group 2 and group 15 that give them a higher ionization energy than we would expect them to have. Let's look into why. As I said, this element number 4, I should say, is beryllium. This element number 12, is magnesium. They are both in group number 2. Because they're both in group number 2, they're going to have the same number of valence electrons, and their valence configurations are going to be the same, albeit off by an energy level. So I overdid that one. The outermost electrons are in the 2s, and here they're in the corresponding 3s. Now, if you remember about s sublevels, an s sublevel can only hold 2 electrons. It is then full. We can think of it this way, that the electrons paired in their opposite spins like this are very stable. And whenever you're very stable, more energy is required than normal to disrupt you. More energy is required than normal to remove one of those electrons. So because of the stability that the atom gets, the configuration of the atom gets, thanks to having a full S sublevel, outermost S sublevel, these have higher ionization energies than we would expect. And it's a similar story if we look at group 15 elements. It's not exactly the same, but it's very similar. In group 15, we have, of course, N, and we have P. They have the same valence configuration. In the case of N, 2s2, 2p3, 3s2, 3p3 in the case of P. If we take a close look at the p orbitals, in both cases, they're identical. The p has 3 orbitals, and 3 electrons mean that each of the 3 orbitals has 1 electron. So it appeals to us in a way how balanced, how evenly distributed every single electron is. Remember, these are all negatively charged entities, so they're going to want to be as far from one another as possible. If you keep in mind that each of these orbitals is a dumbbell-shaped region, they're all at 90 degrees from each other. I mean, you have to imagine that what's coming, this, what I call the Z, is going into the board and is coming out of the board. So all these are 90 degrees from each other. That's pretty much as far as one electron can be from another. They're very, very stable as a result. And so we can say the following, that a half-filled P subshell, in this case in the outermost P subshell is half-filled, because it's so stable, more energy will be required. So it's all about either having, in the case of the group 2 elements, a full outer S sublevel, or in the case of group 15 elements, you have a half-filled outer P sublevel. This confers a good deal of stability and therefore higher ionization energies than we would generally expect. The next point deals with ionization energies other than the first ionization energy. Let's take a look. As I said, if you are an atom like, we'll say, carbon, well, carbon has 2 electrons in the first energy level, and 1, 2, 3, 4 electrons in the second energy level. If I want to remove that electron, it takes a specific amount of energy. But then each other electron that I have to remove has its own energy. They always increase. As I remove one, it's harder to remove the next one. So in the case where I had 6 electrons in this atom, I have 6 different ionization energies for carbon. Now, again, ionization energy, as I reminded you here, is the amount of energy needed to remove a given electron. So not just the first. We're dealing with the first, the second, the third, the fourth. Every single electron having its own specific ionization energy. I want to make some generalizations first. I can recognize my valence electrons. These are the outermost electrons because they have a relatively low ionization energy. By contrast, kernel electrons, those that are deep inside the atom, closer to the nucleus, inner electrons, have generally high ionization energies. I've given an example here with lithium. I'm going to accompany this with a sketch. Lithium's an easy one to draw. It has a nucleus with a certain nuclear charge. It has two occupied energy levels. We know from our ref tab that it's 2-1, meaning I have 2 electrons in the first energy level and 1 in the second. Now, I've said here that if you're lithium, that is the ionization energy for the outermost electron. It takes 520 kilojoules to remove 1 mole of electrons from a sample of lithium. Now, once I remove that outermost energy level, I'm getting down into the core. The core is much closer to the atom, to the nucleus of the atom. And as a result, it takes more energy, and a lot more energy, 7,298 kilojoules per mole, to release this electron. I keep saying that, I apologize. To remove that electron. Once I remove that electron, turns out that, for reasons we don't get into, this electron is allowed to drift closer to the nucleus. And because it drifts a little closer to the nucleus, it takes even more energy to remove. That's why successive ionization energies always go up and up and up and up, each as we go deeper and deeper and deeper and deeper into the core. Well, what we want to be able to do here is that this is our task. If I give you all of the ionization energies for a given element, the place where you see an enormous jump in ionization energy is the place that is the dividing line that separates the valence electrons from the kernel electrons. So let's take lithium, because we just spoke about it. Notice the first ionization energy, as we saw, was 520. The second is 7,298. The third is 11,815. Notice, there's no doubt about it, although there's an increase from the second to the third, it pales in comparison to the gigantic leap. What is that? Maybe 11 times, 12 times greater than what it was originally. Probably, possibly more. I should know, I didn't calculate it. Where I find that place of enormous jump is where I have made the transition from the valence shell, again the lower energies, to the kernel. Meaning that once I remove this outer, remember I probably didn't do it justice when I drew it, the kernel is this, the valence shell is much farther out. Once I remove that, that's the low energy. Now I'm into the kernel, and it takes these amount of energies to remove this. So this is like in the direction of removing electrons, removing into the kernel. So based upon this, I see that there is one low number relative to the other numbers. That must mean that there's one valence electron in the atom, and group 1 elements always have one valence electron. Let's move along down the list of atomic numbers. Beryllium. The first is 899, the second is 1757, 14,848, and then 21,006. Again, this is a big, big jump here, but I'm not even doubling this. This is the big jump. I'm increasing this probably about at least 8 times. This is about 8 times greater than that is. So that means that these two, there are 2 low energies, and that means there are 2 valence electrons. So that means group 2. For boron, notice the big jump is from the 3rd to the 4th. That means there are 1, 2, 3 valence electrons, meaning it's in group 13. For carbon, I increase, but then I take a giant jump upwards from the 4th to the 5th. That means there are 1, 2, 3, 4 valence electrons. That must be group 18. And jumping ahead to the last one, oxygen, there's a steady increase, nothing too dramatic. Oh, yes, we're increasing by about 6 times here, if my math is about right. 6 times greater. That means that these are all considered relatively low. 1, 2, 3, 4, 5, 6. 6 valence electrons. That means this element is in group 16. Okay? So you have 2 skills explaining the variation in, or the exceptions to the general trend in first ionization energy. And in this one, I have to say goodbye because I've run out of time.